All right, guys, so what we're going to be looking at here, and this is a big change from the previous unit we looked at, but what we're going to be looking at here is what is known as graphical analysis. Now, as a brief overview of what graphical analysis is as far as a free response question goes, most of the time you are just given some sort of graph, and you're asked to find a variety of things about that graph. And so the hard part about these, number one, this is always done without a calculator, so you don't have your calculator, and that's not a huge issue. The harder thing about these problems is that you look at them and you're like, I don't know what that's asking me to do. Once you understand what it's asking you to do, these are actually some of the easier problems that exist on the test. The problem is it's really hard for you to figure out exactly what you're supposed to do. So what we're going to do is we're going to go over these different ideas. Again, you'll be given a picture of a graph. And sometimes it's the original function, sometimes it's the first derivative. Every once in a great while it's the second derivative, although honestly that doesn't happen very often. So let's take a look at each of these different, what's happening. And I'll go through this a little bit quickly if you ever need to pause to write down the things in the boxes, because there is an awful lot of definitions that we're going to talk about here. Make sure you write those down, and then we'll get to what's going on, like in an example, okay? So if I was told I have a graph of the original function, and I was asked to find a critical point. A critical point is asking you where the first derivative is equal to 0. So you would take the first derivative, and you would find out, and you would set it equal to 0 and solve it, okay? And again, that's more if you have a function. If you have a graph, it's a little bit differently, because all it's asking is where is there a max or a min on that graph. They almost never ask that, okay? So don't worry too much about that. This is if you have a function, you take the first derivative, you set it equal to 0, and you solve it. If you want to know where a point of inflection is, you take the second derivative, and you set that equal to 0, and you solve it. So again, not the first derivative, but the second derivative, you set it equal to 0, and you solve it. If you want to know where the original function is increasing, you basically make that sign chart that we've talked about, where you find your critical points, you put them on a number line, then you plug in numbers that are on either side of it to find out where it's positive and where it's negative. Wherever it's positive, it's increasing, which means wherever the first derivative is negative, that is the original function is decreasing. And anytime you're asked to prove that, you can't say, number one, you don't have your calculator, so you have to prove it without a calculator by setting the first derivative equal to 0 and then solve it, okay? So here's a couple more questions. Like if I'm asked to find a maximum, what we do is just like we talked about before, this is again with a function. So we have a function, not a graph. I take the derivative, I set it equal to 0, I find my critical points. A critical point on the original function is where the first derivative changes from positive to negative. So if the problem asks, how do I find a maximum, and you don't have a calculator, you take the derivative of the function, you set it equal to 0, you find your critical points, you put them on a number line, and a maximum is where the first derivative changes from positive to negative, and you need to indicate that as well. Like once you don't just say the number, you need to say that's where the first derivative changes from positive to negative. If you're asking for a minimum, you do the exact same thing, but you're looking to see where the first derivative changes from negative to positive. Where the original function is concave up, we do the exact same thing as we talked about before, where we take the second derivative, because the second derivative tells us concavity. We make ourselves a sign chart where we put our points of inflection on the number line, and then anywhere the second derivative is positive, that's where the original function is concave up. And where it's concave down is where the second derivative is negative, using that same test. And this is the stuff, when we were going through graphical analysis originally, these were all the things that we talked about. So this should be somewhat of a review for you. Okay, so that's how we find all of those things. Now, to be 100% honest, usually on the AP exam, they don't give you a picture of the original function. If they actually give you a picture of the graph, it will almost always be a picture of the first derivative. Like I'd say 99.9% of the time. I can't guarantee it, but that's what I'm guessing they're going to give you, is a picture of the first derivative. Now, what we have to realize is if they ask you to find any of these things, a relative maximum, a relative minimum, a point of inflection, or an absolute max or min, that is not asking you to just look at the graph and say what's the highest point and what's the lowest point. they will be asking things about the original function based on the fact that we have the first derivative. So if I want to know where a relative maximum occurs, I just look at the graph and I say, okay, where does that graph cross from positive values to negative values? Wherever that happens, we have a relative maximum. If we want to find a relative minimum, we try and find out where this graph that we're looking at crosses the x-axis from negative to positive. Okay, so again, you're looking to see for either of those, you're looking to see where the first derivative graph crosses the x-axis. For a point of inflection, what we're looking for is where the first derivative has a max or a min. So you'll see graphs that go up and down like this, up and down. Everywhere that those graphs have a max or a min, that's where the original function has a point of inflection. Okay, and that's how you justify it. Because if you think about it, that means the first derivative went from increasing to decreasing at those points, which means the derivative of that went from positive to negative or vice versa, which would cause the second derivative to change sign. Absolute maxes or mins are, I'm not going to lie, they're probably going to be like the bane of your existence. The reason why I say that is they by far take the most work. Basically what you have to do if you're looking for an absolute max or min is it's telling you to find the very highest point or the lowest point on a graph, and they'll give you like an interval that you're looking at. The problem is when they ask you to do that, you need to check a whole bunch of different places to find out which is actually the highest and lowest point on the graph. This is what is known as a candidate test, and when we do a candidate test, we basically say, okay, I'm going to look at the endpoints. So all of the endpoints are possibilities for an absolute max or a min, because the graph could start at the highest point or the lowest point. And anywhere the derivative graph, and this is important, anywhere it crosses the x-axis. So anywhere this graph crosses the x-axis of the first derivative, that's a possibility of having an absolute max or a min. Once you do that, you actually have to go and find the y value on the original function, and we'll talk about how to do that in a few minutes. But you need to find that as well, and then compare all the y values, whichever one is the highest, that's our absolute max. Whichever one's the lowest, that is our absolute min. All these other ones right here, if I want to know where the original function is concave up and I have a graph of the first derivative, I find out where f prime of x is increasing. So anytime the graph is moving in an upwards direction, the original function would be concave up. If I'm looking at where the first derivative is decreasing, and I have a graph of it, that is where the original function is concave down. Okay? You could as well, if you actually had the function, take the derivative of the first derivative to get the second derivative and set up a sign chart like we've talked about before. Now the next one is, let's say again I'm doing that candidate test that we talked about previously, and I want to know the value, the y value at the original function. Okay, and that should say x equals b, not time equals b. This is very much the same as asking for the position when we were talking about particle motion. You take your initial position, which is the y value, and they will give you that at a given x value. Then you do the integral from a to b of the derivative, and that will tell you what that y value is at that time. The problem again here is we don't have a calculator, so you have to do all that by hand. It takes a little while. If I'm looking for the second derivative value, and we've talked about this briefly, but if I'm looking for the second derivative value and I have the first derivative, what I'm basically going to do if I have a graph, is I'm going to find the slope of the graph at that point. Now, a lot of this, you're probably saying, okay, I can do that. All of those things sort of make sense. I get it. The problem lies when we actually, and there is one more thing. I don't want to skip this. What happens an awful lot on the test is they'll give you this integral, and then they ask you questions about something like, it'll say like g of x is equal to the integral from 0 to x of f of t dt. It'll say something like that. And then it'll ask you a whole bunch of questions about g. Well, what that's really saying is, like, I need the derivative, and they'll only give you a graph of f as well. So you won't know what g looks like. We'll have a graph of f, and then they'll start asking you a bunch of questions about g. Well, what we have to realize in this case is I need to know that g prime of x is equal to f of x. In other words, if I take the derivative of g of x, that's like taking the derivative of this integral, which means really what I'm looking at, and you'll see this in the problems a lot, what you're really looking at is that g prime of x is really f of x, so I have a graph of the derivative that I'm looking at, and you can deal with it from there. I know that's kind of confusing, but if that is the case, you need to state this somewhere in your problem so that you can get full credit for the problem that you are looking at. Okay? So, and I'm actually, the second derivative, if you have a graph of the second derivative, this is just real quick. To find a point of inflection, you just find out where that graph crosses the x-axis. If you want to find where the original function's concave down, you find where the second derivative is negative, or where the graph is below the x-axis, and where it's concave up is where that second derivative is positive or above the x-axis. I went over that just real quickly because almost never do they give you a graph of the second derivative. So if you want to pause it for a second, write those down, that's fine. I don't even know if there's a space in your notes for that, but that's just something that you might need to know, but doesn't really show up on AP test questions. Okay, so let's take a look now at an example problem. So this is from 2005, so it's from a while ago, but all of them are very similar. You'll know you're looking at a graphical analysis problem almost immediately because you're given a picture of the graph, and it's just got line segments or possibly semicircles. That happens every once in a while as well. And you'll notice in these problems that the introduction, there's almost no introduction at all. It's just, here's a graph of f that consists of 3 line segments. And that's it. There's no other introduction to the problem. It's very difficult to say, oh, what was I given versus what I want in this problem as well. That makes it very, very difficult to give you any sort of context as to what's going on. So that is what we have in this problem, okay? So let's take a look at letter A. Now, these problems are very important to understand, that we read it and understand exactly what it's asking us to do. So this says, let g be the function given by g of x equals the integral from -4 to x of f of t dt. Now, what we have to realize, and this is going to be true, we are going to be asked a whole bunch of questions about g, but I don't have a picture of g, I only have a picture of f. When I think about that, I'm like, okay, this is a picture of f, how are they related to each other? Well, what I would almost always say to do in these instances is take the derivative of g, and that tells me that what I'm looking at here is really a graph of the derivative, which is what we discussed. Now what we're going to do is we're going to be like, okay, if that's the case, we know already what that's telling us, what we're really looking at a picture of the derivative graph. So now that we know that, we need to find g of -1. Now you have to realize what that's telling you to do. All that's saying here is take -1 and put it into g of x. So when I do that, I remember the x was right here for that -1. I put that in for x, and I get the integral from -4 to -1 of f of t dt. Well, what that's asking us to find is the integral from -4 to -1. It wants to know the area of that shape. When I do that, okay, there it is shaded in right there. You just find that area, you're good to go. So that is just a trapezoid. So it'd be like 1/2. I've got -4 plus -3. I apologize, plus -2. Then we multiply that by how wide it is. It is 3 wide. And you're done. You actually don't have to simplify that or anything. You leave your answer like that, you're good. Okay, so that's your answer for the first one. The second one wants to know g prime of 1. Now again, what that's asking us to do is, it wants us to take the derivative of g and plug in -1. Well, the derivative of g, we found that already, that is the g prime of x is equal to f of x. So this is a graph of the derivative. Since this is a graph of the derivative, that means I just need to take -1 and plug it into this graph and find out what the y value is. So it turns out the answer to this one is that it is -2. Then you're all done. That's it on this one. You just look at the graph, not knowing that initially, but it's just asking you to look at the graph and tell what the function value is. The next one wants us to find g double prime of -1. So really, again, we're asking what is it that we need to find here. This is a graph of the first derivative. I need to take the derivative of this. So that's really asking us to find the slope of the line. So really it wants to know what is the slope of the line passing through the point x equals -1. Well, the problem here is that as I look at that, there is a corner there, so we would say that g double prime of -1 does not exist. There's not a slope there. There's two different slopes. We have to try and decide between them. That's not going to happen, so we find out that that one does not exist. Now, again, it's really easy a lot of times as I'm walking you through them to say, okay, I get that, but trying to come up with this stuff on your own is a little bit more difficult, so don't get frustrated. Let's take a look at letter B. Letter B says, find the x coordinate for each point of inflection on the graph. Well, of g. Well, again, realize this is a graph of the derivative, so what I'm looking for, according to my definitions, is where this graph has a maximum or a minimum, like an actual max or a min. That is at x equals 1, so I would just have to say x equals 1, and then we just have to write it. So we would just say that because we know this is the first derivative and there is a maximum there, we would just, and again, we do need to state this somewhere, we would just say there is a maximum on the graph of f, and always specify what graph you're talking about. Don't just say the graph. You say, okay, there's a maximum on f. That means that g has a point of inflection at that point. So you just say at x equals 1. Part C, okay, and I guess we talked about this already. Okay, we already talked about that. Okay, so part C says, find all the values for which h of x equals 0. So h of x is a brand new function. We're not talking about g anymore. Now we're talking about h. H is the integral from x to 3. So the integral is going to stop right here, and we want to know what are all the values that we're going to plug in that is going to make this integral be 0 for x. So what number am I going to put in right here? Well, whatever number I put in, it's going to find the area from that number to x equals 3. So when you think about it, what I'm basically trying to say is where are the positive and negative areas going to cancel out? The first number that I can see is at x equals 1. The second number that I'm going to see, and you can trust these straight lines. On a lot of other graphs, you can't trust exactly what they're showing, but on the straight lines, you can definitely trust. I can see at x equals -1 as well, that if I put that in for x, that would make the positive and the negative area cancel each other out. And that's what all these things are going to say, okay? So that is the answer for letter C. And luckily, we don't have to justify it. We just have to say where it happens, and we're good to go. And that's what oops, and I put that's the wrong triangle. That triangle should be up there. I don't know why I filled that one in. So don't worry too much about that. Come on, there we go. Okay. So we talked about all that and why those would be the answers. So letter D says, again, we're looking at that same integral, the integral from x to f to 3 of f of t dt, and we want to know where h is decreasing. Well, in order to do that, you just want to know where the first derivative, h prime of x, is less than 0. Well, if I take the derivative of this, I get negative f of x, because that x is on the bottom. So when I take the derivative, in order to really take the derivative, I need to flip the x to the top, which would make the whole thing be negative. So really what it wants to know is, this is a graph of the derivative, but it's been flipped upside down. It's almost like this the graph of the derivative of h really looks like this. So what I want to know is, I want to know where this graph is below the x-axis, because that would tell me where the derivative is negative. Well, that happens from x equals 0 to x equals 2. So x equals 0 to 2. So I would just say from 0 to 2 is where h is decreasing. And the reason why I know that is h prime of x is negative on that interval. Now again, I know we went through that kind of quickly, and as soon as I kind of explain it, it makes sense. These problems are difficult because it's just pure math. There's nothing going on with the context of the problem where I can be like, okay, I get that this is a rate, or I understand something's moving forwards and backwards. No. Every one of these is a problem asking you to interpret most of the time it's a derivative graph, and that's difficult. Like, I get it. It really is hard. So don't get frustrated. Make sure that you ask all the questions that you need to, and that's just covering it right there, and we talked about this as well. Okay, so that is one example. Now again, these will be frustrating. Don't get upset when it doesn't make sense. This is the one unit where it really, really, really pays off to ask questions about what's going on. So if you have any questions about this or anything else, please let me know.